So we found the Laplace transform of a function of t, that function being e to the at, and we got, as a result, a function of s, which is 1 over s minus a, but we notice that that only exists if s is bigger than a. So a natural question to ask is, can we take the Laplace transform of any function? And the answer is only if the integral converges. So is there an example out there where the integral will never converge? Let's find out. Okay, so let's look at this function e to the t squared. Something that you should notice about e to the t squared is that it's going to grow really, really quickly. So if we take the Laplace transform of e to the t squared, that's going to be the integral from 0 to infinity of e to the minus st times e to the t squared dt. Okay, now that's going to be the integral from 0 to infinity of e to the, I'm going to combine the two e's, so e to the t squared minus st. And then I'm going to add and subtract s squared over 4. Now, why would I do that? Well, in fact, I'm trying to complete the square. So I'm going to factor out an e to the minus s squared over 4. And then what's left is e to the t minus s over 2 squared dt. So you might say to yourself, now how could I possibly do that integral? Well, the first thing I'm going to do is I'm going to do a substitution. So u I'm going to let be t minus s over 2, and du is then dt. So that becomes e to the minus s squared over 4, the integral from minus s over 2, so t equals 0 gives you u being minus s over 2, to infinity of e to the u squared du. Now my next step, the next thing that I'm going to do is I'm going to split this integral up into two integrals. Okay? The first integral is going to be the integral from minus s over 2 to 1 of e to the u squared du. Now, I don't know how to do that integral, but I do know that the function e to the u squared is continuous from minus s over 2 to 1, so I do know that that integral exists. The second thing I'm going to look at is the integral from 1 to infinity of e to the u squared du. Now, I'm not sure whether that integral exists or not because it goes to infinity. Okay, so what would be left? Well, I would have e to the minus s squared over 4 times, okay, my first integral isn't really going to change. It's from minus s over 2 to 1 of e to the u squared du. Okay, but now I want to use that theorem that I had before. So I want to compare this function, e to the u squared. In particular, I know that e to the u squared is going to be greater than or equal to e to the u on that interval from 1 to infinity. So instead of saying equal, I'm going to say that that integral from 1 to infinity of e to the u squared du is greater than or equal to the integral from 1 to infinity of e to the u du. Now, hopefully, with a quick computation, you're going to see that this integral, the integral of e to the u, as you go from 1 to infinity, that's not going to converge, right? That's going to go to e to the infinity if we were to work it out. And of course, that doesn't converge, okay? So the integral that we're looking for is greater than or equal to infinity. So it does not converge using that comparison theorem that we looked at earlier. So the Laplace transform of e to the t squared does not exist because it does not, that integral does not converge. So now I'm trying to think, do we have any sort of criteria that tell us when this Laplace transform thing is going to exist? Okay, so suppose that f is a piecewise continuous function on the interval from 0 to a for all a greater than 0. And we're going to say that f of t is bounded by k e to the at, meaning it can't grow any faster than that exponential function, a constant times e to the at. And that only needs to be true as long as t is greater than or equal to some m. A, k, and m are all constants. K and m are positive. Okay, the theorem says that the Laplace transform is of f of t is going to equal some capital F of s, and that it'll exist for all s greater than a. Okay, so why would that be true? So let s be bigger than a. Then, if we looked at the absolute value of the integral from 0 to infinity of e to the minus st f of t dt, we'll recall back from calculus 2 that that would be less than or equal to the integral from 0 to infinity of the absolute value of the inside of that integral, e to the minus t, and then also the absolute value of f of t dt. Okay, well, that's going to be less than or equal to e to the minus st is positive, so the absolute value of it's positive, so I'm just going to write e to the minus st. But f of t in absolute value is less than or equal to k times e to the at dt. Okay. So that's equal to k times the integral from 0 to infinity of e to the minus s minus a t dt. And you'll note that we actually did this integral before, so we get k over s minus a. That was the integral that we did before, as long as s is bigger than a. And that value, of course, is less than infinity. So since the absolute value of that integral converges, then the integral itself converges. And that proves the theorem that says that as long as f is piecewise continuous and it does not grow faster than an exponential, okay, that it can be bounded by a growing exponential function, then the Laplace transform will exist for all s bigger than a. Okay. Let's move on to one more example of finding the Laplace transform. Let's try to find the Laplace transform of a function that maybe is a little bit more interesting. Let's try to find the Laplace transform of sine of at. Now, this is going to be the integral from 0 to infinity of e to the minus st sine of at. Now, you may say to yourself, now, how do I do that integral? Okay, well, we're going to look at doing it by parts. So we're going to let u be e to the minus st and du equal minus s e to the minus st. What's left is dv, which is sine of at. And so v is going to be minus 1 over a cosine of at. Okay. So what is this going to equal? Well, it's going to be the limit as b goes to infinity of minus 1 over a e to the minus st cosine of AT evaluated between 0 and B. So that part is U times V. And then we're going to subtract the integral from 0 to B of V times du. So V times du is going to be S over A e to the minus st cosine of AT dt. Okay, so that's U times V minus the integral of V du. Okay, I'm going to make one little change, and I'm going to pull the S over A outside the integral just to make it a little bit easier. Okay. Well, this first part, as b goes to infinity, e to the minus sb is going to go to 0 because s has to be positive. So what I'm left with is just going to be 1 over a from that first part. Okay, but to do the second integral, I'm going to need to integrate by parts again. Okay, so I'm going to do the second integral, I'm going to do u equals e to the minus st, and du equals minus s e to the minus st. dv is going to equal cosine at, and then v would be 1 over a sine of at. Okay. So let's see, I get 1 over a. I'm going to subtract the limit as b goes to infinity of s over a times, now I'm going to do that integral. Okay, so it's u times v. So it's 1 over a e to the minus st sine at evaluated between 0 and b. And then I'm going to get minus the integral from 0 to b. And then I have a minus s times 1 over a. So that's going to be a plus s over a e to the minus st sine of at dt. Okay. Now what's going on here? Okay, so we get 1 over a minus, let's see. First, notice that with this term here, that as b goes to infinity, e to the minus sb is going to go to 0. Okay, but also if I plug in 0, sine of 0 is going to be 0. So everything that I've underlined there, that's going to all go to 0. Okay, so what I'm left with is s squared over a squared, and then another integral, e to the minus st a of t dt. But hopefully you'll notice that that's the integral that I started with. So in fact, what's sitting over there with that integral is actually the Laplace transform of sine of at. Since we have the limit as b goes to infinity there. So the Laplace transform of sine of at is equal to 1 over a minus s squared over a squared Laplace transform of at. Of course, we're assuming here that s is bigger than 0. So in fact, I'll just need to solve for the Laplace transform of sine of at. So I can write this as the Laplace transform of sine of at times 1 plus s squared over a squared. So I'm going to move everything with the Laplace transform over to the left, and then I'm left with 1 over a. So that tells me that the Laplace transform of sine of AT is equal to 1, let's think about this, it's going to be 1 over a times 1 plus s squared over a squared. And that would be a completely, perfectly legitimate way to write this. But most people like to multiply by a on the top and the bottom so that the Laplace transform of sine of AT is equal to a over a squared plus s squared. And you will likely need to find the Laplace transform of cosine of AT for your homework.